Good afternoon, everyone. So welcome back to the workshop afternoon session on day 2. So what we have done so far is we have covered the aspects that we normally um, take care of in the development of the first law and the zeroth law, uh, and the sequence that has been discussed often now is what has been pointed out. So there are a couple of topics which we are skipping, of course, from the lecture series, but those lecture videos will be made available to you anyway, wherein before we start with the discussion on second law, a couple of weeks almost are spent on engineering fluids and specifically the ideal gas model and the related quantities, and also the water steam system with an introduction of steam tables is done. And primarily the reason for that is uh, based on the material that has been covered up to the end of zeroth law, including the first law. When the discussion on these engineering fluids is done, there is a scope of generating sufficient number of problems for practice using the first law and the work interaction and so on. And that is what we do. Of course, in this workshop, we are not discussing those two intermediate topics in some sense. So let's move on to the second law discussion that we can do now. So to get going, usually to the students, what we point out is that the first law and the zeroth law tell us what happens when a process is executed, but they don't tell us whether that process itself is possible or not. And that is the issue that is handled through second law, is how we normally begin the discussion of the second law. And then a little bit of discussion on the historical development is also done. I think you have probably seen that in Professor Gaitonde's lectures. And then we point out that there are several possible statements that one can utilize to introduce this second law. And we have chosen to use the Kelvin-Planck statement as the primary statement in some sense of the second law. And as the development takes place in the next several lectures, a few other statements of the second law are obtained as a consequence of using this Kelvin-Planck statement in a few specific situations. So that's how we normally progress. And here in the current session today afternoon, we will look at introduction of this Kelvin-Planck statement, introduction of what we call a heat engine. And there is a specific terminology that we associate with the heat engine. One thermal reservoir heat engine, two thermal reservoir heat engine. So one THE, two THE, etc. is what you probably have seen already. And then a temperature hierarchy is formally established through the use of the Kelvin-Planck statement of the second law as applied to a sequence of heat engines. And then, before we proceed, we also introduce then the reversible process. Before we actually formally introduce the Carnot theorem, we introduce the reversible process, the notion of a reversible process. So up to that is what we would like to cover here in the afternoon session. And first I'll request Professor Bhandarkar to add to this, and then we can proceed with any discussion and specific points that you would like to point out. Thank you.
Thank you. So, of course, this is regarding the second law, and it is kind of very tricky because different textbooks put forth different statements of the second law, and by far the most dangerous statement that people put out there right in the beginning is that the entropy of the universe increases. Okay, students have no clue what entropy means, and they don't have any clue what the universe means, and then they are supposed to deal with this statement, and it's a very bad way to introduce this concept and the second law, and leads to a lot of confusion. And hence, just like for the first law, there were many statements and we chose the one which makes the most logical sense. We go here and choose the statement which makes the most logical sense, and then every other statement which is supposed to be for the second law, we show that they are all equivalent to the first statement that we made. And the first statement, okay, just like the first law is a generalization for systems which undergo adiabatic processes. You can say the second law is the way the Kelvin-Planck statement is stated is a generalization in many ways to systems that undergo cyclic processes, where we say that any system which undergoes a cyclic process cannot just purely absorb a fixed amount of heat during this cyclic process and deliver the exact same equivalent amount of work. Actually, you can more or less stop at purely absorb, because in a cyclic process, whatever you absorb as Q has to come out as W. Net Q is net W, and what you are saying is you cannot just purely absorb heat during the cyclic process, because that all comes out as W, and that is simply not allowed as far as the second law of thermodynamics is concerned. So you just need to reject some amount of heat during a cyclic process, and that becomes a compulsion. So then every other statement that we make is shown to be equivalent to this statement till we come to the Carnot theorem, which is again a statement of the second law. And then we come to the Clausius inequality, which finally leads us to trying to define this property, or we figure out that there should exist a property, okay, of a system, okay, which does not change when a certain kind of process occurs, let's say. Okay, so that is when we define the property, just like we used the first law and defined a property called the energy of the system if the process was adiabatic, and then generalized it. Similarly, we will define the entropy for reversible processes and then generalize it, and then we will come up with a term or a sort of mathematical equation or the second law, where we also introduce a term called as production of entropy. So this is in a nutshell the way we process. I will just tell you the steps that we normally follow in a fast way again, okay, so that the logical way we go. We first lay out the Kelvin-Planck statement, then we define heat engines, and we show that a 1T heat engine cannot exist. Then we use the 2T heat engine to define a hierarchy of temperatures. In between, we also look at the Clausius form of the second law and show that it is equivalent to the Kelvin-Planck statement. Then we move out to the Carnot theorem and we introduce reversibility. Okay, and we show that all reversible 2T heat engines operating between the same two temperatures must have the same efficiency, and they must be higher than any other 2T heat engine operating between the same two temperatures. Okay, and then we come to the Clausius inequality, which leads us to this property called as entropy. So that is the kind of steps that we take to ensure that the law is stated in a way that it is irrefutable, and then we each of the further statements is derived, or you postulate that this has to be equivalent. If it is not equivalent, then you show that the original statement is violated, and that is how you move forward till you actually posit that there should be a property known as entropy. So that is how the argument processes. So I will now ask Professor Gaitonde, because since he has developed this method, he can, if I missed something or said something wrong, he can tell something.
Okay, Upendra, you have said everything correctly. I can only say that I selected this route. This is not the only route that we can proceed with. There are other routes, But I selected this route because I find that not only is it logically neat, it is something which an engineering student can appreciate, because we are talking about heat, conversion to work, engines, cyclic processes. And this will be good for the student not only in this course, but in later energy conversion or applied thermodynamics courses as well. That's it.
Yes, so anyone now who have come up with some ways in which they want to explain this, or face some problems in how they explain, or come up with some problem or some kind of device which they think explains to students a concept better. Now I think the floor is open.
Yeah, I see there is one comment from Professor Vednath Mathur. Maybe I'll request him to try to explain what he means by that.
Actually, if I want to state Kelvin Planck's statement, then I'll have to make use of the terms heat engine and efficiency and all those things. And until and unless I explain heat engine and refrigerator and efficiency and COP, it's difficult to explain the statement and the equivalence of a statement. So should we go for explaining the terms reservoir, heat engine, COP, efficiency, and then we define the statement of second of thermodynamics, or it should be done the other way around?
Okay. Professor Gayatri, you want to take that, or should we? I will probably say how I look at it. So the second law statement, I don't know why you require the heat engine and the reservoir and anything like that. Let me tell you how we put the second law statement. It is impossible for any system undergoing a cyclic process to purely absorb an amount of heat during the process and deliver an exact equivalent amount of work. So this is only a system undergoing a cyclic process. There is absolutely no talk of a heat engine, a temperature reservoir, or anything like this. Those are subsequent steps that we take to develop the hierarchy of temperatures. Then we bring in the Clausius statement only because the Clausius statement uses high and low temperatures as if it is known, whereas we show what high and low should mean under the ambit of thermodynamics, and only then we bring in the Clausius statement when we show what high and low means as far as our first statement goes. And then we bring in the Carnot theorem and the Clausius inequality, and then forward the property of entropy. So this is how we proceed.
Yeah, that is exactly the sequence in which this material is presented.
Most of the time, we state Kelvin Planck statement as like a engine cannot have 100% efficiency. So this require understanding of engine and.
So basically, you went from the system undergoing a cyclic process to an engine. So, I mean, if it is presented like this, yes, we agree that some kind of engine definition is needed. But, you realize you don't have to present it like that. You can just talk of a system and a cyclic process. That's about it.
Yeah. Thank you, sir.
Sir, then how can we explain in application wise, sir, except engine, other than engine?
The question is not clear. What does it mean? You want, of course, every law you have to apply to some places, correct? Are you talking about applications later on?
Yes.
So, I mean, what stops us from applying a law to any application that we need? I'm not sure. Sorry, I'm not sure what the question means really.
No, sir. That is, we are telling Kelvin Planck statement with engine because we are supplying heat and it is not exactly converted into work output. So likewise, similarly, how can we explain, sir, any other applications? Anyway, we are telling all the cyclic processes.
So
we are very much comfort with engine. That's what I am telling you. How to do in other way.
Okay, again, unfortunately, it is not clear. So see, that's what we are saying. We don't bring in the engine right in the very first statement because we just want to talk about a general system. Okay, because you realize that all the laws are made for general systems, not for specific, purposes. Once we define a system undergoing a cyclic process and amount of Q and amount of W, then you can go ahead and define an engine and then make it more interesting as you want. And then you can show, you can make an equivalent statement and say, see, there is something called as a heat engine. This is what a heat engine does. It is supposed to deliver a positive amount of work by taking in some amount of Q. And then you say it, by this law, it cannot just take in the Q and deliver it entirely as work. So it has to reject heat somewhere, and hence it cannot be 100%. So those are steps you have to take later on. Okay, don't just jump into the engine is what we are saying.
Yeah, Professor Vanjara, Dr. Vanjara, you can go ahead, please. And then Professor Gaitonde can respond.
Sir, whether it is a Carnot statement or Clausius or Kelvin Planck statement or this latest one, which I have not ever heard about, Karathodius statements, but all of them are conveying the same meaning with some keywords are there in each statement. The concern is, sir, I was not getting this last one from the point of view of Karathodius statement that you will not be able to change the state in some nearby region. Is it possible to clarify it in detail?
Okay, let me take over here for a while. One,
yes, sir.
The form of Kelvin-Planck statement which is used there. One reason is that we want to develop a Kelvin-Planck statement with as little additional definitions as possible. So if we can develop a proper and cogent Kelvin-Planck statement without talking about engine efficiency, refrigerator or heat pump and then coefficient of performance, why not do it? The current statement, the one which we use of Kelvin-Planck statement, requires our understanding of obviously first law, heat interaction, work interaction and cyclic processes. That's it. Okay. Then the second question is about Karathodius statement. Now, Karathodius statement is another approach to second law. Okay, if you can start with Karathodius statement and then derive everything else. However, as I said today morning, it requires a lot of mathematical detail and to which engineering students and most of us are not exposed to. But the effect or the result of Karathodius statement can indirectly be obtained as a consequence of Kelvin-Planck statement. These are all equivalent in the sense that if you select Kelvin-Planck statement as your primary statement, among the derivations will be Karathodius statement. Okay. And if you start with Karathodius statement as a primary statement, then from its derivations, one of the derivations will be Kelvin-Planck statement. Okay. But if you take the starting point as Kelvin-Planck statements, then the consequences and derivations are such that number one, too much mathematics is not needed. Two, we will be using terminology with which most engineers, particularly mechanical engineers, are comfortable, and hence the learning process will be that much easier.
Yeah, so just to summarize what Professors Bhandarkar and Gaitonde said, the way the Kelvin-Planck statement is put forth as the primary statement doesn't make any reference to an engine per se. It simply talks about a system which is undergoing a cyclic process. Now, a cyclic process is something that we have already defined earlier in the course, and therefore students should be aware of what is meant by a cyclic process. And also the system which is undergoing the cyclic process here will have certain heat interactions and work interactions, and those also have been already defined in the previous part. So in that sense, the form that Professor Bhandarkar read out of the Kelvin-Planck statement doesn't make any explicit reference to a heat engine per se.
So if I understood it correctly, we'll have to explain the statement using a cyclic process without mentioning about engine, etc. So heat transfer in the cyclic process
Correct. So
cannot
you
be equal
can
to
simply
the
say that, yeah, we simply say that consider a system which is undergoing a cyclic process, which has certain number of heat interactions and work interactions involved. And for such a system, the Kelvin-Planck statement states that it is impossible to purely absorb a certain amount of heat and deliver an exact equivalent amount of work. That's all.
That's correct. Thank you, sir.
Of course, we never said that you must do this. It is just that we are just following a series of steps which we think is logical without involving too many external definitions. But if you think you can make something interesting but still make the correct statement, I think it's fine. It shouldn't be a problem.
So another equivalent way of stating the Kelvin-Planck statement without, of course, resorting to any reference to engines, etc., can be something like this. And I think we do this as well. It's impossible for a system with heat interactions to undergo a cyclic process without rejecting heat. This is another way of stating it.
So actually, before going to the formal statements of second law, what I thought we should first give some examples of the heat engine. Like through Rankine cycle, we can just demonstrate about the components of a thermal power plant, including boiler, turbine, condenser, then pump. Then we can say that this combination will make a closed cycle, and in that way we can get some work output. So likewise, we can include some example such that before going to the statements, the people should have proper imagination of what is called as the heat engine and working in a complete cycle.
Again, you could do that. What we have been trying to point out is that the specific Kelvin-Planck statement that is used to introduce the second law, in any case, doesn't make any reference to a heat engine at all, the way it has been done in these set of lectures. So from that point of view, we think that there is no necessity yet to invoke any idea regarding heat engines and so on. I think that's what we are trying to point out. Professor Bhandarkar, please.
Yeah. I mean, you see, if you want to introduce a topic and motivate people to learn, that is enough. In the real world, you can always present. There's no harm in giving a preamble on, see, this is why this topic has to be studied. Otherwise, we will blindly put 3-4 statements and say study this and go. Correct. So I think it is fine. Whatever you use to motivate something is up to you. I mean, and then as long as you are following a consistent set of arguments, there should be no problem. That's all I think. And if you really want to motivate students, there is people even now, I can tell you, they come up with these schemes where machine is continuously operating and generating energy continuously without any input of energy. These so-called perpetual motion machines, and even now people come and tell us, see, I have brought this scheme up and this will continuously operate and keep on generating energy, and can I file a patent on it? I mean, see, all these laws of thermodynamics are based on what we observe, and it seems that people still don't observe, and then they come up and make such statements. Okay, so the thing is, you can give a lot of examples from the past where people have tried to do things and they have not worked specifically because of certain things, how nature operates, and that is how those laws have been distilled and made into these concise statements, and we are just using some kind of logical set of statements to ensure that there is no ambiguity. That is all we can state. Yeah.
Yeah, so the effort here in developing these lectures has been to build on something that has already been done in the previous part of the course. So if you have noted how this progression has gone, so far. We are utilizing only the bare minimum information that has been, clearly described and defined earlier in order to formally state this Kelvin-Planck statement. But otherwise, as Professor Bhandarkar said, if there is a need to make students interested. So of course this goes back to what I think Dr. Vanjara had pointed out yesterday. There are two aspects of pedagogy as we agreed yesterday. One is making students interested in the subject, which is what we were not really looking at in this workshop. We were looking at the other aspect, which is developing a subject from a certain logical point of view to make it least ambiguous and as clear as possible to the students. But I understand that there is a possibility that, a requirement that you have to bring in some real life applications in and out to make students interested. Deepen Banoria, please go ahead.
Sir, my question is arising to explain the concept of entropy, which is related to some engines. If we take because a mechanical engineer, especially the first and the second year, are very keen to know how the thermodynamic concept has been applied to the automobile engineering, because automobile are very fascinating and very eye-catchy to the new and the young era. So how can we explain the concept of entropy with related to some engine and basic automobile concept?
Okay, so you directly want to connect this concept of entropy with the engine right from moment one. I would suggest please do not do it, because that will lead to a lot of confusion. All you can suggest is that just like I think I don't remember, Professor Junaid said he brings in Rankine cycle to motivate the talk about what can be done and not done. You can talk about IC engines, and because IC engines are also heat engines, and as far as we are concerned, they are really good piston cylinder systems. Okay, and you realize you can always tell that this is the amount of fuel you put in, this is the amount of energy that goes in, and yet this is the amount of work that comes out once the entire one 4-stroke cycle has been executed. Okay, so that means some amount has been rejected, and that is part of the second. When we come to entropy, please do not talk of entropy right now. Okay, this you can only say, this is what second law is all about, and then once we come to entropy and cycle analysis, you can talk about entropy at that. But don't bring in entropy at moment one. Is what.
Right, sir. Right. Thank you, sir.
Yeah. So as the material gets developed. In fact, Professor Bhandarkar had given a complete overview of how this second law related material gets developed. Once the Clausius statement and later the Clausius inequality is introduced, the notion of entropy is brought out from there. So this is, in response to Professor Mathur's question. We bring about the notion of entropy once the discussion on Clausius inequality is done or it's going on. That it automatically comes out of it.
Usually it's difficult for the student to understand that concept about integration of Q reversible by T is less than equal to greater than 0. They already have in their mind from their physics courses that there's something called disorder, which is connected with the entropy.
Correct. So I think we make an effort here to inform the students that they need to get rid of those notions from their mind, regarding any disorder and so on. It may or may not be that easy for us to achieve, that, but nonetheless we still do that.
So I think probably, what the problem is that a lot of times people attempt to give these so-called physical explanations for certain terms, and they think that they are making the matter easy by giving a particular explanation. And unfortunately, those so-called simple explanations stick in the mind, and later on they create confusion. And this is what this entire business of disorder or just blindly talking about entropy brings in. So that is a problem we all struggle with. Unfortunately, even after teaching, hammering a lot of information, some students just don't want to let go of that. And then, if you are not ready to let go, it is very difficult to put in a different kind of information. And then it becomes very obvious that if you ask a question which is slightly different, those students definitely get confused, and that confusion is arising from those previous thoughts that they don't want to let go. So I agree, it's very difficult to get some people to throw out those thoughts, that nothing can be done about it.
Two quick comments from me. Physics with Akshay. I am actually not aware of the term that you are referring to in the chat box. So at least I am not going to be able to address that. Sanjay Geji, I do not know. I haven't read Professor Achyutan's way of introduction of second law statement. But at least the way you have written out here, and of course Professor Gaitonde can correct me, the reference to conversion of heat into work on this continuous basis probably refers to the cyclic process that we have been talking about. And complete is, again, cannot be complete, meaning that, again, going back to that same notion that there has to be certain amount of heat rejection that has to happen. And I think that's what I think those words are referring to. But I will request Professor Gaitonde to comment on that. Yeah, I haven't seen the original paper. Yeah.
Let me say something. This complete and conversion, both complete and continuous conversion of heat into work is an old, method of explaining, and we can take care of that by using a system which does not undergo a net change of state. It may execute a cyclic process and then work with, then come up with the Kelvin-Planck statement. Okay. A complete and continuous thing comes when, for example, you can have a process. A simple, very simple example is the expansion of a gas, assuming it to be almost an ideal gas. If we execute an isothermal process, then, and if it is an expansion, it will absorb energy in the form of heat from a reservoir, and it will do positive amount of work. This is complete conversion, so-called, of work into heat. But remember that this is not a cyclic process. The system has to expand. And the question is, how long will it keep on expanding? At some stage, that expansion has to stop, because there will be some physical limit on that cylinder or whatever contraption you are going to use for this so-called complete conversion. So if there is a limitation, so naturally at some stage you have to stop, and that means it will not be a continuous conversion. Moment you have to stop, you have to bring it back to some original state. So you have to execute a cycle, but then to bring it back to the original state, you will have to expend some work. That brings us back to the cyclic process. So it was an older method of saying what we say in a simple current form of Kelvin-Planck statement. By the way, anybody who is talking about Professor Achyutan, he was one of my teachers, one of the major teachers of thermodynamics. But whatever he presented in his book is only part of our story. Further thought processes, further discussions with Professor Achyutan have led us to the current structure which is presented in this set of videos. Thank you. Back to Puranik.
Yeah, so I think it will be good to discuss this question from Junaid. The thermodynamic temperature scale, and for that I hope you have seen the lectures, Junaid. we first introduced the Carnot theorem, and the efficiency of an engine is something that has already been also introduced. And on the basis of that, we realize and put forth to the students that the ratio, if you can imagine, of course, the notion of reversible process has also been introduced, and the reversible cycle is being discussed the moment we get into the Carnot theorem discussion. The ratio of the amount of heat rejected to the amount of heat absorbed is then shown to be a function of the two temperatures of the reservoirs between which this reversible heat engine is supposed to be operating. And once that is brought forth, then we do some further manipulations, in the sense that we propose a certain form of that function. And I think I will request either Professor Bhandarkar or Gaitonde to talk about that, because they will be able to articulate it far better than I can.
No, Professor Gaitonde, I think you can.
What are the specific questions? Because in the chat room and this thing, there are physics with Akshay says it was in his original paper. Which original paper?
No. Professor Gaitonde, we are talking about Junaid's question related to the thermodynamic temperature scale.
Oh, the thermodynamic temperature scales, this will occur after Carnot theorem.
Yes.
And the Carnot theorem will give us a handle to develop a scale of temperatures. Now we call it thermodynamic because the Carnot theorem, remember, characteristic of Carnot theorem, or the the derivation of Carnot theorem does not depend on property of any material. Whereas all the temperature scales which we have set up using zeroth law require an intermediary called a thermometer. Okay? So it has to be a mercury in glass, it could be alcohol in glass, it could be a long solid extending, or a bimetallic strip bending, or it could be an ideal gas changing its pressure at a constant volume, or changing its volume at constant pressure, and such stuff. Whereas the Carnot theorem gives us a handle to develop a scale of temperature based on purely a reversible cyclic 2T heat engine. No material. Material can be anything. That's one of the strong points of Carnot theorem. And that gives us a scale of temperatures independent of any material, purely based on principles of thermodynamics. Hence we call it thermodynamic temperature scale. Now the question about the absolute temperature scale, this is historical thing. We don't use the word absolute temperature or absolute zero or something like that. This was used in the earlier days, because in the days when Celsius and Fahrenheit and others developed their empirical temperature scale, the zero on that temperature scale of arbitrarily defined. Celsius used the sort of standard or laboratory developed ice point for standard water. And Fahrenheit wanted to have a zero at a lower temperature, so I think he used a eutectic mixture of ammonium chloride in water. That was the easiest way for him to create a slightly lower temperature with as little effort as possible. But then when people started studying the behavior of gases, then Boyle's law was discovered, and the ideal gas law was discovered. And then they realized that, the pressure volume product of a gas depends of an ideal gas, or a gas at low pressure, which behaves like an ideal gas, depends only on temperature. And that can be used to define a scale of temperature. Then the question arises that, look, on this PV product, how low can you go? And then they realize that if you define a parallel scale to a Celsius scale, then on the Celsius scale at approximately minus 273 degrees, the PV product of an ideal gas will go to 0. Now that was a very interesting thing for experimental physicists, and they said that, look, there must be some idealization in this because there must be a limit. This seems to be a physical limit, perhaps a thermodynamic limit, and hence they said that will be an absolute limit for the lower end of temperature, and hence the idea of an absolute temperature scale and an absolute 0 turned up. Any supplementaries? Otherwise, let it go back to Puranik and Bhandarkar.
Yeah, I think what I will definitely suggest to Junaid and others, of course, is to again go through the specific set of lectures which deal with this idea of introduction of a thermodynamic temperature scale. But I think Professor Gaitonde has given a clear overview of what has been done in that sense. There is a question from Sanjay, which I think I'll ask him to explain more if he can unmute himself and go ahead.
Hello, sir. Sanjay here.
Yeah, go ahead.
So my question is because all this second law, most all the statements, KP statement and Clausius statement, these revolve about the cyclic devices. They mostly talk about cyclic devices. So so applicability of a second law is only limited to cyclic devices, or the need for cyclic devices is to obtain the continuous operation. Cycle can operate on a continuous process. So it is only because of our limitation to have this machine in a cyclic form only, or we cannot have any single one-shot process on a continuous manner. Is it the limitation?
I think my understanding is that, of course, I will request the other two to comment on this, but my understanding was that the Kelvin-Planck statement is, introduced with reference to cyclic systems, and maybe you can even add heat engines to that. But then later it is generalized, so it is not necessarily limited to only cyclic processes. So, Professor Upendra?
No, Professor Gaitonde has raised his hand.
Oh, yeah, okay, go ahead.
See, the cyclic device is used because we want as direct a link possible, as direct a link as possible between a heat interaction and a work interaction. If you use a non-cyclic device in between, then that Q will not be algebraically equal to W. It will be W plus delta E of that system which is executing that process. By enforcing the intermediate system to be a cyclic system, we can enforce that delta E is 0, and hence Q directly is related to W without any third middleman coming in. And this helps us with the derivation till we come to a stage that we have to apply it to a process. Then all that we do is let that cyclic process be split into two sequential processes, and from there we develop things for individual processes, non-cyclic processes. So starting with a cyclic process is only a first step. Sooner or later we are going to break open that cycle and derive things for a non-cyclic process.
Yeah, I'll request Professor Bhandarkar to address the question on entropy and statistical mechanics.
Oh, okay. See, I think we don't want to bring in statistical mechanics here. But you should realize the definition of terms don't really change. They are just shown to be equivalent. Okay, so You should not think of anything different from here, because what happens when you bring in statistical mechanics is people start talking about this disorder and number of ways to do things, and it's a lot of confusion unnecessarily. So let us not get into that.
Yeah, as far as this specific course is concerned, as an undergraduate introductory course, possibly biased more toward mechanical engineering students, we really try to avoid talking about anything from statistical mechanics when it comes to entropy. I think that it adds a lot of confusion, and it can simply keep on going without really no end to it as far as students are concerned. So we generally try to avoid it. So of course, in this set of lectures, which we are currently discussing roughly, the notion of a reversible process has also been introduced. So I would like to ask somebody to comment on that part regarding reversible process. Yeah, Professor Mathur, you can go ahead.
One of the question which a student usually asks is the difference between a quasi-static process and a reversible process.
Correct, and this is what I think we had mentioned yesterday as well, that we will wait till we go to the discussion of second law and related matters, that we will take up this point. Now that in this set of lectures, when we have formally introduced the reversible process, then this aspect can be addressed. And so the answer to this really is that a quasi-static process need not be reversible. On the other hand, a reversible process must be a quasi-static process. So this is really the bottom line. But I would like to ask why this should be, based on the understanding of quasi-static process and later now with the reversible process being defined. And to answer Junaid's question very quickly, no process is ever reversible. So again, it's an idealization and an abstraction that we utilize for performing analysis to at least obtain some useful predictions based on which we can carry out further calculations. That's all that is to it, really. So an example normally we can provide when it comes to a process being quasi-static but not reversible is oftentimes you can invoke that standard piston cylinder problem with gas contained in the cylinder, and if it is expanding, let us say, if we are in a position to claim that at any stage during the expansion we are in a position to uniquely state the value of the properties such as pressure, temperature, volume, etc., then that process is going to be quasi-static according to our own definition, the way we had defined it. However, if there exists a frictional component, say, between the piston and the cylinder walls, then that whole business becomes irreversible. So here is at least one example where the process is quasi-static, but then it's not reversible. Professor Bhandarkar can add to this and with anything else that he wants to.
Yeah, so this is regarding quasi-static and reversible. Is that how you are saying?
Yeah.
Okay. Okay, because I was seeing a comment. I think Professor Gaitonde has already.
No, that's for
commented. Yeah, that's for something else. Okay, so the way reversible is defined in books, I think Professor Gaitonde addresses it differently. I mean, if two systems are undergoing a process and then they can actually come back to their original states without involving the third system or changing the state of a third system, then you can actually say the process was reversible, because no one would know that the first process actually took place, because everyone seems to be back to their original state. So that would be the way we should look at what a reversible process is. So you realize that no process that we know of actually, is like this. So if you have a hot bowl of water, you keep it outside. Okay, it cools down, and then if you need to bring the water back to boiling temperature, you need to involve the stove again and bring it back. The atmosphere is just not automatically going to come back, be in its state and heat the water by itself, okay, and bring it back to its original state. So reversibility is defined in this way, but what you should realize is that, if you want to get a reversible process, you need to get through a set of, it so happens that you need to get through a set of equilibrium states, and that necessarily implies that you had to undergo a quasi-static process. So both of these are just hypothetical contraptions that we will continuously use to define certain terms. They don't really exist, but the concept of reversibility requires the concept of quasi-staticness, and whereas a quasi-static process, for example, you can have a hot body and you which is like at 100 degrees centigrade, and you put a thick insulation, okay, and the process can be quasi-static. Every step would be in equilibrium. You can measure the temperature everywhere in the hot body, and outside it is cooling down. You can always measure it, but it is never going to be reversible. So you can have a quasi-static process which is not reversible at all. Okay, so that is the distinction that you need to make.
Thank you, sir. Now I got the explanation, the main difference between quasi-static and reversible process.
Yeah, it is very important to clarify this to the students as well. And with these couple of examples that were just described, I think it should be reasonably clear.
Yeah.
Thank you. Yeah.
Thank you.
Yeah, so there was this one intermediate part in these set of lectures on the establishment of the hierarchy of temperatures, and that's something that, in my opinion, again is quite interesting and unique way of establishing that. I don't think you will see that in any standard textbook. So any comment on whether that was appreciated, and if that is going to help you in explaining some of these aspects to the students? Yeah, I think Dr. Vanjara, you have raised hand, so please go ahead.
Sir, actually, not only that temperature hierarchy, but also I already stated in the chat box that the concept of 1T and 2T heat exchanger that is used throughout for deriving many things, that is also very unique and interesting. The students can be exposed to this 1T and 2T heat engines in such a way that for everything, ultimately, if it violates Kelvin Planck statement, then we do not accept it.
Yeah, that's exactly right. In fact, that is what I will answer Sanjay's comments, really, with exactly what Dr. Vanjara was pointing out. So the Kelvin Planck statement is utilized first to show and set some sort of a yardstick, if you wish, that it is not possible to have a 1T heat engine, and then all subsequent arguments are one way or another reduced to have this 1T heat engine, and then we show that because 1T heat engine is not possible due to Kelvin Planck statement, some of the later parts are then proved in that fashion, using the 1T heat engine idea. Yeah, so as Professor Gaitonde has already written, the 1THE, 2THE are used to simplify the calculus, because everything then can be worked out in terms of algebra. If you had so-called finite reservoirs, then the analysis becomes more complicated, and that's what Professor Gaitonde is pointing out right now in the chat box, that with the use of these 1T and 2T heat engines, all concepts can be worked out with only algebra, and you don't have to bring in any other level of mathematics to it. That is correct. Yeah, thank you.
Also, I don't know why Sanjay has posted the same question. Professor Daitonde has already replied to it. There is, you are talking of proving Kelvin Planck statement. There is no proof. I mean, it's a statement based on our observation. So don't make a statement that we are proving. Then none of the laws can be proven. They are only our observations. Okay? So they are just statements which tell our observations. What we are showing by this series of steps is that two statements are equivalent. So that is how we are proceeding with the other statements. So please
Yeah,
look at
that's
it like
actually
that.
an important point, really. Exactly. Keep that in mind, that other statements are not getting proved. They are simply being shown to be equivalent to the Kelvin Planck statement, which we have chosen to use as the primary statement of second law. Yeah, thanks. If you have something to say, please go ahead. I think there are two raised hands, Sanjay and Vednath Mathur. Go ahead, please.
Sir, may I please?
Yeah, go ahead. Go ahead.
Sanjay here. Yes, that was my question regarding 1T heat engines. So regarding 1T heat engine, yes, that logic is very, very useful, and I found it really interesting. And I have actually seen Gaitonde sir's lectures about 10 to 20 times till the point I could really understand it. Still, the one question still remains that about the Kelvin Planck statement. He straight away made a statement like this, that 1T heat engine is not possible. That is what he meant to say. So he directly jumped on that, or was there some thinking behind it? That is it related to that the same concept that heat cannot be and continuously converted into work?
Yeah, that's it. So it's a direct
Is,
consequence of the Kelvin Planck statement. That is correct.
so is that so that heat conversion of heat into work, direct complete conversion of heat into work is not possible? So is it based on the experiment or based on the observation?
Same thing, right? Experiment is essentially observation. So this statement is, a law because no real life experiment or situation has ever contradicted it. So it is based on experiments, or you can call it observations also. It's the same thing.
Because various arguments have been made while showing how this Kelvin Planck statement gets violated when we come to show that any all type of combinations come to 1T heat engine turning out to be 1T heat engine, that leads to a violation of a second law, or a violation of a Kelvin Planck statement of a second law. This is how this logic, we start at one point and we again come around the circle and end up at 1T heat engine. So okay, that's
So
well
yeah, so
convinced.
another way of looking at it is that the Kelvin Planck statement and the direct consequence of it, that a 1T heat engine cannot exist, has been essentially utilized as what we can call a trump card. Okay.
Yes,
So
yes.
we keep coming back to it, and we keep coming back to it when we want to show that something is not possible. Okay.
Yes, yes.
That's how
Yes.
it's getting used, if you notice. Yeah, fine.
No, that method is highly convincing, and we also get even students get convinced about that. But that basic question glitch was remaining at the back of mind, that is it so for any cyclic device to convert heat into work continuously, so it has to reject anyway, it has to reject some amount of heat.
Yes, that is the absolute bottom line. That is correct.
So heat engine can never have 100% efficiency. Heat engine never. Okay. Just one more. Just extend. I want to extend it a bit, but again, I think it may not be proper time because we have not yet defined the thermodynamic temperature scale. Am I right? So
well, it's been discussed already, the thermodynamic temperature scale, as a consequence of the Carnot theorem.
Yes,
we discussed it a few minutes ago.
yes. Thank you, sir.
Yeah, Professor Mathur, you have a raised hand.
It's regarding showing equivalence of Kelvin Planck's statement and Clausius's statement. Usually we start with one statement, and using some logic or algebra, we say that violation of this statement leads to the violation of the other statement, and hence these two statements are equal. Now, can there be a simple method by which we can say that one statement, instead of saying violation of one, leads to the violation of another, which is not very well appreciated by student? So they say, okay, if this statement is true, then by some logic we should lead to that this statement leads to the second statement also. Instead of saying violation, can there be some method?
So let me say something, and I think I have mentioned this in the series of lectures.
Yes.
See, traditionally all books, engineering thermodynamic books, have take great pleasure in showing saying that there is a Kelvin-Planck statement of second law based on engines, and the Clausius statement based on, say, refrigerators. Let's keep away from heat pumps just now. They are just refrigerators in a different pair of clothes, set of clothes. But one thing I have said, and again let me emphasize, that the Kelvin-Planck statement does not bring into it the idea of a higher temperature and a lower temperature, because at most you need one temperature reservoir, but actually the basic Kelvin-Planck statement does not talk of any reservoir at all. Okay? Whereas Clausius statement talks of a refrigerator, it talks of a lower temperature to a higher temperature. But in thermodynamics, we have not yet, even after the Kelvin-Planck statement, defined what is a lower temperature and a higher temperature. Hence, we do not consider the Clausius statement as a proper candidate for a possible statement of the second law of thermodynamics. We consider the Kelvin-Planck statement as the only primary statement of the second law. And then, as developed in the video lectures, we proceed, we show that there is a hierarchy of temperatures. We formally then consider what are to be higher temperature, what are considered to be lower temperature in a comparative way. And then we can define refrigerators, and then we can show that the so-called Clausius statement is a proper derivation from the Kelvin-Planck statement. So I would like you to get away from the idea of equivalence of these two statements. For equivalence, they have to be at the same level of, seniority or ability in thermodynamics. They are not. Clausius statement is a secondary statement. It's a derivation from the Kelvin-Planck statement. Keep that in mind.
But most of the book uses this thing that a violation, they start with Kelvin-Planck statement and reverse one of the engine, and they say that now see this leads to the violation of Clausius statement.
Yes, but for that it is already assumed that you know what is a higher temperature and what is a lower temperature in a thermodynamic sense, which is sort of jumping the gun. So it's some sort of a circular argument, which we don't want to get into. Hence we say let's start with Clausius statement, and step by step we go on deriving, and we find that one of the derivations is that all temperature levels are not arbitrary. There is a hierarchy, and then by convention we decide one end of the temperature to be higher, the other set to be lower. And then after that we can show that, look, proper derivation is Clausius statement.
Okay, thank you very much, sir. I think I'll have to go through your video lectures.
Yeah, that is what I will certainly suggest. It's actually quite well developed in the lectures. So please do view those. So as anyway, we are required, we meaning the participants are required to submit as part of the graded activity. Yeah, Achintya, will come back to you in a minute. One thing that needs to be thought of on this set of topics as well is what sort of a question or possibly a problem even that one can one can generate to test the understanding of students on this. With that, let me ask Achintya Kameli to go ahead with what he has.
So what happens is that a lot of students, they are quite enthusiastic, and they often look at a lot of online material, and inevitably they end up on the concept of entropy. I understand that the next session we'll be talking about entropy, but how do we navigate, avoiding entropy while talking about KP and the Clausius inequality? So if there's any guidance that you could provide regarding that.
Yeah, so if you go through these lecture videos carefully, you will realize that the method in which this entire second law material is developed goes in such a manner that when we begin with the Kelvin-Planck statement, there is absolutely no reference made to this property called entropy. It's not even needed. Okay, all that is needed when the Kelvin-Planck statement is put forth as the primary statement is the understanding of a system which is undergoing a cyclic process, which is what we already know. And while executing this cycling process, there are a bunch of heat interactions and work interactions involved. That's about it. So with that, in our opinion at least, that there is no real reason to think about entropy in any manner. And you can actually point this out to the students, and we do that as well. If going through this sequence and developing this material in the manner that is getting done, if some students do ask such questions, at least I tell them that let's wait till we go to the Clausius inequality, and then, as Professor Gaitonde just mentioned a few minutes back, while discussing that cyclic process, we break the cycle and then introduce the notion of entropy. And it typically works out fine without any problem. Yes, we do understand this, and of course we have experienced this as well. As you correctly said, students seem to read from all sorts of things without oftentimes understanding the implications. And it's a little bit of a task to keep informing them that this is not the place where you need to bring this idea in and so on. It's required.
Sir, actually, we have conducted a few internal tests as a part of the grading methodology, and one student actually brought up the 0-point energy and concepts of that sort. So it was actually quite a challenge. So I was just hoping that we could get some input of how to navigate this field. So that's all.
Yeah, I mean, I think Professor Bhandarkar has more experience on this, so maybe I'll ask him to comment on it.
So I didn't get it. What was the question? 0-point energy?
So the question which we had raised to the students was come up with a hypothetical device which violates the violates the first law and does not violate the second law. So basically, we are just figuring, just asking the students to come up with creative ways of working around the problem. And so the students then after naturally, since this was online examination, unfortunately they took to the internet and came up with a lot of creative ideas, including 0-point energy, which is quite an advanced concept, to be frank, sir. So that was a problem which we were facing, sir.
Oh, okay, so I don't know what they actually brought in, so it becomes very difficult to comment unless I know how they brought in the 0-point energy and what they did with it to explain. So unfortunately, I don't know how to answer this question.
Okay, sir. No. Actually, I was not, looking for an answer for the 0-point energy, sir. I totally understand that.
No, you are saying how to handle the situation. I guess that is your main question.
Yes, sir. Yes.
I mean, see, of course, if students bring in whatever creative inputs, that's very good. We just note it down and we try to see on the spot. It's very difficult to give any answers to some concept that they've read elsewhere. Okay, and we will probably need to think over it and figure out how is the best that we can remove any kind of ambiguity in their mind. So that I agree. I mean, it's not going to be an easy task at all. So let us agree on that. So
we also find it hard to address these kinds of issues. And oftentimes we will end up saying that let's wait till we formally introduce the notion of entropy and so on. Depending on the student, it is accepted reasonably or not, to be honest with you.
Sir, what exactly happened when we go to the class to start with a lecture of second law of thermodynamics, and say we just start asking that who knows second law of thermodynamics, then students used to say two statements. The first, very common, that heat flows from higher temperature to lower temperature, and the second, which everybody is telling, that entropy always increases. So, sir, my question is, what happened actually? These two are so frequent statements, but we do actually derive these statements later on. So it's our task to rather orient them in such a way that we have to start with Kelvin Planck statement and all these things. So that also becomes a task for us in the class, that how to do it.
Yeah, I mean, that is totally agreed upon. I mean, the fact is that people are taught many things in 11th and 12th, and they have heard many terms. So one of the things that we keep repeating is, we try to figure out what all they know and what all they have, what all concepts they seem to know, or let us say they just know. I mean, whether it is correct or not is something else. So once we make a set of these concepts that have come out from their understanding, when we start teaching, we tell them, see, most of you are thinking in this fashion, but these can lead to such and such ambiguities and such problems, and hence it is best to forget it at this time and take this material which is being presented to you logically. So that is the only, I don't know if that is the only way, that is one of the best ways, I would say. In fact, Professor Gaitonde does in the very first lecture take a kind of zero quiz. He asks, he passes a sheet on to many students and asks them to list down certain things which automatically bring forth whatever they seem to think about the subject based on their 11th and 12th standard knowledge. And then you can keep a record of all those concepts that they seem to be having in their mind, and then hopefully one by one, as you start teaching something, you can say, see, this is why such a concept should not be kept, or such and such an understanding is wrong, because this is the kind of ambiguity it leads to, and so on. So it's a good practice to just record all the kind of concepts that students bring with them from their past lectures, and then go ahead and address each of those. That's all I can say. Yeah.
Okay, thank you, sir.
Hello.
Yeah, please go ahead.
Yes, it's regarding my question of sequence, whether properties of steam should be taught prior to second law of thermodynamics or not.
I say something I think I have already posted.
Yeah.
See, the property relations are not really required for development of the first law, second law. Okay? However, if we keep away from properties, then in a engineering course, it becomes difficult to set up problems, get a physical, realistic feel to the students. That's what we have to do for engineering students. Hence, as required, we will keep on inserting property relations, properties of steam, of refrigerants, etc. as needed. But for development of the concepts of thermodynamics, they're not really needed. And that is why in this pedagogical discussion, notice that we have skipped those 2 weeks in between lectures. I think the topic number 5 and 6, I think we have skipped.
Yes.
They are there, you can always refer to them. But you will notice that even if you skip them, the second law development which follows does not suffer at all.
Yeah, so the continuity will not be lost even if you skip those and go directly to the second law discussions. But obviously, in a at least in a system like IIT where we do continuous assessment, there are a bunch of exams and other things that go on. For those purposes, it is very useful to introduce those properties of steam and ideal gases and so on, so that whatever material has been developed till the end of zeroth law, including the first law, can then be put in the form of problems and so on. And that's all that really I wanted to convey as well.
In fact, I met an old professor of physics. He said, your set of videos is good, but he said those parts B and D or something, which essentially one part pertain to properties of steam and the last 2 weeks which were pertaining to open system. He said, what do they have to do with thermodynamics? They only distract from the main thing. That is a physicist's way of looking at it. But that will not be an engineer's way of looking at things. Right? If for mechanical engineering students, in even a basic course in thermodynamics, if we do not mention steam as a working fluid, air as a working fluid, and if we do not mention open systems, it will not be a course in engineering thermodynamics.
So, if I have to design a syllabus, should I keep this properties part at the end, or it should be kept somewhere in between first law and second law?
I think a good idea is to keep them parallelly. With first law, you sort of introduce some properties. With second law, you introduce more properties. But bring in the introduction of steam tables or something like that as early as possible in the course. Okay. But impress on them that this is a parallel stream, which we need because it is useful. But it is neither necessary nor sufficient, that sort of a thing.
Thank you, sir. Thank you.
Yeah, so Professor Mathur, of course, when we want to try to solve problems using the first law statement, there will be a requirement of evaluation of change in the energy and so on. The delta E that shows up in the first law. In order for that to be done, these property introductions and the calculations of those properties and the differences between them and so on, using say steam table and so on, will be very useful. And that's the reason we, in some sense, parallelly introduce it and carry on with the remaining part later.
Yes, thank you very much, sir.
So let me ask a question then as a general question to all participants. So in your experience, is this topic, namely the second law and related ideas, considered to be the most tricky part of this thermodynamics course, or is there something else? So at least one response is that this is the most tricky. Yeah. So yeah, I would very strongly suggest to go through the lectures 20 to 32. This is the set of lectures which address the second law and related topics. And it will probably take some careful working out of things and so on to understand and appreciate many of these issues, but 20 to 32 are the ones that I will strongly suggest. So to answer Junaid's question, so we have roughly 40, that is 40 clock hours assigned for a one semester course. So that's really yeah. So some of those we utilize to conduct, of course, possibly small tests and quizzes and so on. But by and large, 40 hours clock hours are available. Yeah, this comment from Girish Undale on the availability part. So as you notice in this set of lectures, the availability idea has not been explicitly taken up and addressed. So maybe I will request either Professor Bhandarkar or Gaitonde to quickly comment on that.
This availability and exergy, I have tried to sort of demystify them. If time permits, whenever I have taught thermodynamics, once in a while I get a week or so in which I can do that. There is nothing special about availability and exergy. It is only the combined application with some structure of the second law and the first law to a given system and a given set of processes. I think I have a lecture video somewhere. Maybe I'll try to find out and provide a link. It was recorded in 2009 in my live classroom and is available under the CD PenPTEL scheme. I'll just check out how to get it and give you access to it. I have noted this and I'll try to do this in a day or two. Just keep on looking at the discussion forum of this course, which will be available, I think, even after the course is over for quite some time. So I will provide the link out there. Over to Puranik.
So are there any other comments related to classroom experience when dealing with this topic? We will be, of course, continuing with this second law tomorrow morning as well, where we will talk more on the Clausius inequality and the introduction of entropy and the use of entropy as far as our engineering calculations and understanding is concerned. But in the meanwhile, if you have any other comments based on the topics that we are discussing presently, please go ahead. Yeah, let's go in the sequence. Let's say Professor Mathur first and then Dr. Vanjara later. Is that fine?
So, I had this question in the morning also, which was replied, but just want to repeat it. So it's the way we define entropy. So it's good if we are teaching to the student, then we develop it after Clausius inequality with all those mathematical expression. But suppose it happened with me, I faced the interview, and there in the panel, probably there were type of people from physics background, chemistry background, and mechanical engineering background also. And when they asked me the definition of entropy, I could not able to explain using Clausius inequality. So can there be a simple definition of entropy without involving those integral?
Yeah, Professor Gaitonde, yeah, please go ahead.
Unfortunately, no. Entropy is a derived property, and unlike temperature or pressure, which we can feel, energy, we get an idea because we develop a field, however abstract it is, right from our school days about potential energy. You know, you fall from a height, you get injured because you are suddenly losing that much energy. You get scalded if you touch something hot. So there is a concept of thermal energy. If you run too fast and hit into something, again you get into a problem because you are expending so much of energy. So the idea of energy, temperature, velocity, pressure, these are all palpable things. We can develop some sort of a feel for it. Unfortunately, entropy is not like that. In fact, a few months ago, I had a discussion with an IITB alumnus, friends, actually 2 of them. And based on that, I wrote a small article which I have put on the web. I will provide the link in the discussion forum soon. I know where it is, so I can do it in a matter of minutes before 4 p.m. today. Over to Puranik.
Yeah, just a quick comment on Junaid's question. I really don't know regarding IIT Bombay X versus NPTEL SOAM. So there is a question here, or the comment here, the last one, physics with Akshay. Example of first kind of perpetual machine, second kind of perpetual machine. Exactly what was that supposed to mean? Because we really, in this set of lectures, are not really referring to any of the terminologies that you are mentioning here on perpetual motion machines or perpetual machines. So not sure what we can say about it.
Sir, I have read somewhere that the first kind of perpetual machine that violates first law of thermodynamics, and second kind of perpetual machine that violates second law of thermodynamics. So I want to get more explanation on that.
I think the best person is again Professor Gaitonde to address that.
See, this perpetual motion machine, it's something which is sort of, define something and then say the same thing in a different way. One sort of, this has happened because the idea of extracting energy from something without providing something has been there. It's like the search for, the philosopher's stone, or Paris as we know it in Sanskrit, or the elixir of life, or Amrut. These are because we want free everything. So why not a perpetual, motion machine? Everybody will be happy in a simpler way. Suppose somebody sells you a tank and saying this will give you, drinkable water without any limit. It's just a seed box. Do nothing. You open a tap and you will get water. We will laugh at it because, I can say this is a perpetual drinking water providing system. We know it is not possible because first thing it does simply is violate the conservation of mass. Okay. In a similar way, people have defined perpetual motion machines of the first kind, perpetual motion machine of the second kind. Maybe others have defined of n different kinds. All that the perpetual motion machine one, if you see its definition, it's something which indirectly by definition itself, it violates the first law. It says that without doing anything, without any change of its state, you can extract energy in some form, either work or heat, indefinitely. We know that's not going to be possible because there is first law. The moment you extract energy, the change is going to, the state of the system is going to change, and we have physical limits on physical systems. So if you keep on changing the state, somewhere it's going to reach a limit. So it's going to violate the first law. The perpetual motion machine of the second kind, which is something like an engine, but it sort of either completely converts heat using an engine type or a cyclic device to work, or it does with such a high efficiency that the Carnot theorem is violated, or it is a refrigerator which does work without any work input and works only between two temperature levels. And then we can, rephrase our first law or our second law in terms of a perpetual motion machine. It is only you define new terms and then redefine or rework or reset, formally talk about perpetual motion machines. But invariably, some student or some participant will bring it up. And this is my response today, and it has been my response for I don't know how many years now. Thank you. Over.
Thank you. Yeah, Dr. Vanjara, you had a raised hand, so please go ahead.
Sir, one task is such like if we want to connect different laws of thermodynamics to teach students in class, if we go to the hierarchy of these lectures, we have introduced first law, then we have gone to zeroth law, and then we go for second law. So which one is a better way to go from temperature, or say from the first law of the thermodynamics we go for heat and work to be introduced as a two energy form in transit, and then we introduce heat engines and then to go for it?
Yeah, so the answer really is that, once you have gone through this entire material, you can probably decide for yourself what is the best way, to be honest with you. In our experience, the current sequence that has been put forth in these lecture videos has found a lot of success with students, and students keep repeatedly informing us even later after they complete the second year, go to the third year, and so on, that this course was something that they they highly enjoyed because of the structure that was put forth and so on. And that is what really has prompted these lecture videos to be generated in this manner. So that is really my answer, really, to be honest with you. I'll request Professor Bhandarkar also here.
Yeah, I mean, I think it is very clear that what we are thinking is an okay way to do it, okay? But definitely we are not insisting that this is the only way to do it. You just ensure that whichever way you do, please ensure consistency. So right now you can see the order in which we have presented material. That is a consistent and logical way. You can devise another consistent and logical way, but just ensure that it's consistent and logical and students understand it. So we, beyond stating that our way has worked to a reasonable extent, we can't say that some other way may not work completely, because you may have a very good method of presenting in a different way, but still be logical and consistent. So yeah, you are free to try out various things.
Yeah, thank you, sir.
There was one comment here from Ms. Bhatnagar. Can we use simulation and modeling software for students' better understanding? My answer would be that given the nature of topics that typically go into the first level thermodynamics course, as we are seeing here, the scope for introducing any simulation or modeling software is not much. You could probably do that more in possibly fluid mechanics or even heat transfer course. But you can think about doing it. I'm not sure how it can be done, but yeah, it can be. If there is a way to complement these understandings by using some appropriate modeling or software, yeah, it can be done. Although we have never done it, as far as I understand. Achintya Kamli, you have a raised hand, so.
This is regarding again entropy, if I may bring it up. In many of the textbooks, there's this relation which is the Boltzmann relation for entropy, and yet I've been trying to get to the bottom of this and trying to understand the relationship. Is there any way that we can incorporate this as well in the class, or is it absolutely not required at all? Because this seems like a sort of a simple equation as such.
Required in this class, where we are resorting to what we will call classical thermodynamics or macroscopic thermodynamics. And there is no way you can actually bring that in to even claim that that's going to increase the understanding of students, as far as my opinion is concerned. But I will request here Professor Gaitonde as well as Bhandarkar to comment.
I guess, that's what I said initially. There is this quest to make something more understandable, but unfortunately some of those quests turn out to make things more confusing. So this is one of those, okay? So it is better not to bring in that, because more than anything it enhances the confusion. So keep a classical thermodynamics course as it is right now. If someone else wants a discussion, it is better, to ask them to take a course on statistical mechanics, and they can understand things far better from that point of view. But it is unnecessary, because one guy may understand it better, but everyone else is going to get confused. So it's best not to do it. So this is, of course, speaking from experience. Okay, so that's how it is.
Thank you, sir.
Sir, one question I would just like to ask. It could be a little bit different.
Yeah, please go ahead.
Actually, as a thermodynamic subject teacher, is there any opportunity to publish a research paper? Because it is very difficult for me to get an idea such that I could publish some good quality research paper in this particular domain.
Well, I don't think I'm qualified to answer that question, because as far as research activities are concerned, I have never really formally worked in aspects related to thermodynamics. But the other two instructors, can perhaps answer your question.
Yeah, I don't know what exactly you would like to publish on. You can see that there are many papers out there which are trying to search for the possibility of certain processes, and many of these journals like Applied Thermal Engineering, they are discussing just some regular practical aspects, and they discuss whether it is possible or not using thermodynamic laws. I mean, those are certain things which you can definitely explore if you want. But if you are interested in testing out teaching methods, okay, then there are journals which deal with pedagogy, and if you also are interested in learning about pedagogy, we do have a department or separate center for educational technology, and they kind of have different theories on how things can be taught better. So you can definitely do research in that if you're interested. That's all I can say.
Can there be some simple lab experiments for thermal lab on basic thermodynamics?
Yeah, two things. First one about paper publishing. I think if you look at the course content of a typical undergraduate thermodynamics course in engineering, from the thermodynamics point of view, I don't think there is any scope for a publishing of paper. However, from the pedagogy point of view, what we are doing, you will realize that we haven't yet zeroed on the perfect method. We don't even know whether there is a perfect method of teaching thermodynamics. So as you develop, you can publish papers on the pedagogy, or how to teach or how not to teach, what illustrations to put up. Somebody said, can we create an animation to show quasi-static processes, etc. Yes, you can do that. Something like this I have attempted in a crude way in the video lectures, but when it comes to animations and videography, visualization, the sky is the limit. Okay, so that's where you can create a good output and publish papers. And another thing is, what was the second one which was mentioned just now?
I think any lab experiments.
Lab experiment, yes. Again, going back into history, when I was a student, there was a thermodynamics lab, 6 sessions, alternate week in a 13-14 week semester. But the experiments were not on basic thermodynamics. We used to measure specific heat of air, specific heat of water. Then we used to measure the, develop from 100 degrees C to, or slightly higher than 100 degrees C to near room temperature, the saturation line of water steam using a insulated and an uninsulated pressure cooker. Then we had a very simple method by which we could determine the gamma ratio of specific heats. And we used 2 fluids. One was air and another one was carbon dioxide. And the differences in the gammas were very clearly crude experiments. At that time, we were not forced to or not required to do an estimate of error. The estimate of error would have been significant, but the learning process was really good. Nowadays, even I think soon after I graduated, those experiments and that lab itself was discontinued. I don't think it now continues anywhere else.
Yeah, that is.
But yes, we can set up some good experiments in basics. A few minutes ago, I mentioned that I had written a small article on entropy. A link to that article is already in the discussion forum of the IIT Bombay X course. And I have almost found that not exactly my 2009 videos, but much later videos on availability and exergy. And soon after this session is over, I will edit those links and put them up in the discussion forum.
So quick comment on the last post in the chat. We will of course discuss this tomorrow more, but the second law of thermodynamics talks about entropy and not energy. And this universe is also something that we need to be carefully defining, which will be done tomorrow in the tomorrow morning session. So it's not that astronomical universe that we are referring to, but something else. So we'll take care of that hopefully. As far as the labs related questions were concerned, we do not really have a lab on basic thermodynamics anymore in IIT, at least as long as I've been here. And because of that, I don't have a direct experience on running any basic experiments on thermodynamics material that we are going through. So I'm not sure if I am qualified to comment on the virtual lab either. I do not know what exactly it means, but as long as something that can be designed to reinforce the concepts very clearly to the students, I think it should be fine, I suppose. So we are about to close this session, and what we will do tomorrow morning, again 9 to 11 session, is to continue with the topic of second law of thermodynamics, and we will take up the remaining topics that exist in this, starting with the Carnot theorem, and including the Clausius inequality and the introduction of entropy. And then, as Professor Bhandarkar was already mentioning earlier, we develop a mathematical form which is highly useful in analysis of systems and problem solving for this entropy, and that is what we will be basically doing in the morning session tomorrow.
So Balachandra sir, good afternoon sir.
Yeah, please go ahead.
Sir, actually today activity 1 and 2 I tried to upload sir, but I am not able to upload sir. So can
No, don't worry about that. So don't worry about that part. You just keep that ready with yourself. The graded activities, and I will discuss that part with the course staff, and we will make appropriate changes in the deadlines and so on. So please don't worry about that. It's just that I would request you to have that ready with you, so that whenever those links are working, you can go ahead and upload that. That's fine.
Okay.
Yeah, I think the main important objective of this workshop is to sort of generate ideas for teaching this class effectively, and trying to generate material which we can use to ask students questions on, and that is what that graded assignment part is about. So it's not that critical that even if the link was not working today, etc., don't worry about that part. We'll take care of it. So with this, then let us end the session today, and we will all convene tomorrow morning at 9 o'clock. And as per the provided schedule, we will continue with the remaining parts of second law in the morning session, and end the discussion on second law in the morning session. Thank you.